3.3 Cramer's rule, volume, and linear transformations. For any n by n matrix A and for any vector B in Rn, let AI times B be the matrix obtained from A by replacing column I with vector B. So you have AI times vector B, which would be A1 all the way to B, then AN. Cramer's rule. Let A be an invertible n by n matrix. For any vector B in Rn, the unique solution vector x of A times vector x equals vector B has entries given by the following. X1 would be the determinant of AI, or Xi would equal the determinant of AI times vector B divided by the determinant of A, where I is 1, 2, all the way to n. Use Cramer's rule to solve the following system. So I have this system that I want to write in the form AX equals B. So I'd have 3, negative 5, negative 2, 4, x1, x2 equals 6, 8. So I need to solve for x1 and x2. So I have vector A would be 3, negative 5, negative 2, 4. Vector A1B would be 6, 8, negative 2, 4. Vector A2B would be 3, 5, 3, negative 5, 6, 8. With each one of these, we need to find the determinant of each one of these matrices. So I need to find the determinant of this matrix. And when I do, it would be 2. I need to find the determinant of this matrix. And when I do, it would be 40. And I need to find the determinant of this matrix. And when I do, it's 54. So to find x1, I would just use the determinant of A1B all over the determinant of A. So that would be 40 over 2, which equals 20. And to find x2, it would be, and I just need to fix my notation. The determinant of A2B all over the determinant of A, which would be 54 divided by 2, which would be 27. So x1 is 20, x2 is 27. Let's look at example 2. Consider in the following system in which S is an unspecified parameter. Determine the values of S for which the system has a unique solution and use Cramer's rule to describe the solution. So we're just going to do the same thing we did in the previous example, but instead of having constants as our answers, we're going to actually, our answers will be in terms of our variable S. So you could write down your matrix like we did before, but I'm just going to start by writing matrix A, which would be 3S, negative 2, negative 6S. And A1B, which would be 4, 1, negative 2S. And A2B, which would be 3S, negative 6, 4, 1. We then have to find the determinant of each one of these. And the determinant of the first one would be 3s squared minus 12. The determinant of the following one would be 4s plus 2. And then the determinant of the last one would be 3s plus 24. So to find x1, it would be the determinant of a1b all over the determinant of a. So it would be 4s plus 2 all over 3s squared minus 12. And x2 would be the determinant of a2b all over the determinant of a, which would be 3s plus 24 all over 3s squared minus 12. And you could notice that 3 is common in all of those. So you could factor out that 3 and get x plus 8 all over s squared minus 4. Adjugate a classical adjoint of A matrix of cofactors, also known as the classical adjoint of A, denoted by adjoint A, ADJ, A. Theorem 8, an inverse formula. Let A be an invertible n by n matrix. Then A inverse is 1 divided by the determinant of A times the adjoint of A, or the adjoint of A over the determinant of A. Let's look at example 3. Find the inverse of matrix A. So we need to find all the cofactors first, because then we can find the adjoint of A by using the cofactors. So if I'm going to find the cofactors, I'm just going to start with each one. So C11 would be, that would be going across row 1 and down column 1. So I would have -1, 1, 4, -2. The determinant of that is -2. And then I'd have C21, which would be negative, because when I'm going row 2, column 1, this one would be negative. So 1, 3, 4, -2, and that would equal 14. And C31 would then be positive, and that would be 1, 3, -1, 1, and that would give me 4. Now go into C1, 2. That would be negative 1, 1, 1, -2. That would give me 3. C22 would be positive, and that would be 2, 3, 1, -2, which would give me a -7. And C32 would be negative, and that would be 2, 3, 1, 1, which would give me a +1. And then the last 3, C1, 3, which would be positive, and the determinant of that is 5. C2, 3 would be negative. The determinant of 2, 1, 1, 4, which is -7. And C3, 3 would be positive. 2, 1, 1, -1, which would be -3. So the adjoint of A is the transpose of the matrix of cofactors. So C1, 2 actually goes in the 2, 1 position. So when I'm actually finding the adjoint of A, -2 would stay where it is, but this row becomes the column. So I'd have a 3 and a 5. And then here I'd have 14, -7, -7, and 4, 1, -3. And then to find the determinant of A, I can go ahead and multiply the adjoint of A by A. That will give me my identity matrix multiplied by a factor, and that would give me the determinant because it would be the factor in the main diagonal. And by theorem 8, that would give me the determinant of A. So to show that, I'm just going to do some side work. I would have the adjoint of A times A. So that would be -2, 14, 4, 3, -7, 1, 5, -7, -3 times A, which would be 2, 1, 3, 1, -1, 1, 1, 4, -2, and I would get 14, 0, 0, 0, 14, 0, 0, 0, 14, which is the identity matrix multiplied by 14. So therefore, by theorem 8, my determinant of A equals 14. So now to find A inverse would be the adjoint of A divided by the determinant of A, which would be -2, 14, 4, 3, -7, 1, 5, -7, -13, all divided by 14. So you're going to have lots of fractions. So I'd have -1/7, 1 2/7, 3/14, -1/2, 1/14, 5/14, -1/2, and -3/14. And that would be A inverse. Theorem 9. If A is a 2 by 2 matrix, the area of the parallelogram determined by the columns of A is the determinant of A. If A is a 3 by 3 matrix, the volume of a parallelepiped determined by the columns of A is the determinant of A. Let's look at example 3. Calculate the area of the parallelogram determined by the points -2, 2, 0, 3, 4, -1, and 6, 4. So you could draw a picture of this. And one thing that we could do when we draw this, we notice that we have -2, 2. We can transform this so that -2, 2 becomes 0, 0 to get some new vertices having the same area, making our problem easier. So if I transform this to the right 2 and up 2, this would become 0, 0. This would become 2, 5. So 0, 3 would become 2, 5. 4, -1 would become 6, 1. And 6, 4 would become 8, 6. Then the parallelogram is determined by, so the area of the parallelogram is determined by the columns of matrix A. And that would be 2, 5 and 6, 1. So we're using these two here. So my area would equal the determinant of 2, 5, 6, 1, which would be is the absolute value of the determinant. The absolute value of -28, which is 28. And I I just want to fix my notation here. So we know that this means determinant, but you also need to make sure you take the absolute value of it because area has to be positive. Let's look at theorem 10. Let the transformation from R2 to R2 be a linear transformation determined by a 2 by 2 matrix. A, if S is a parallelogram in R2, then the area of the transformation of S equals the absolute value of the determinant of A times the area of S. If T is determined by a 3 by 3 matrix A, and if S is a parallelepiped in R3, then the volume of the transformation of S is the absolute value of the determinant of A times the volume of S. So let's look at example 4. Let A and B be positive numbers. Find the area of the region E bounded by the ellipse whose equation is x1 squared all over a squared plus x2 squared all over b squared equals 1. So first, we're going to let u1 and u2 be on the unit circle centered at the origin, and let D be the area of the unit circle. Okay, so we need to say let D be the area of the unit circle. Let u1 and u2 be on the unit circled centered at the origin. So then we have A being A0, 0B, and X being X1, X2. So when we have our transformation of U1 and U2, that would be A0, 0B times U1, U2 equals X1, X2. And this is our linear transformation T, remember? So then we know that AU1 equals X1 and BU2 equals X2, or U1 equals X1 over A, U2 equals X2 over B. So the area of the ellipse equals the area of my transformation of D, which is the absolute value of the determinant of A times the area of D, or AB times pi times 1 squared, which equals AB